Inductance. What is it and why should I care? Hello fellow CNCnutz and welcome. Today we're going to be talking about inductance, what it is and how it affects your choice of stepper motor and driver combination. I'm going to start right back at the beginning, back in my school days when I learnt that V equals I times R, also known as Ohm's law. But what does it actually mean? Voltage equals current times resistance. Now, a lot of people are not electrically minded, so what I'm going to do, and I apologise in advance to anybody who hates when people do this, but I'm going to change it to a water-based analogy because it's a lot easier for others to understand. So, voltage is a measure of electrical pressure. It's a potential difference between one point and another, and best considered to be like water pressure. Current is the flow of electrons in a circuit, and in our water-based analogy, it's the flow of water through our, for lack of a better word, we'll call it a circuit. Lastly, we have resistance, and it's exactly what it sounds like. It resists the flow of electrons through our circuit. And in our water-based analogy, we have things that resist the flow of water. In this particular instance, consider it like a pipe. A small diameter pipe has a large resistance, and it's a lot harder to get a decent flow of water through that pipe than it does for a large pipe. And a large pipe has a very small resistance to that flow of water. So for any given pressure, your pipe diameter will determine how much current flows through. In our electrical circuit, for a given voltage, our resistance will determine how much current flows through. So let's give this a bit of a test and see how Ohm's law holds up. We have here a transformer. I'll put my meter across and it's measuring, we'll say 1.8 ohms of resistance. I have here a 12 volt battery, so I'm going to put my meter in series with the battery and I'm going to measure how much current flows through it. So if I take my 12 volts and divide it by my 1.8 ohms, I get a figure of 6.6666 amps of current flowing. So let's just see what happens. That's pretty good, 6.6 amps of current flowing. You can see it's dropping a little bit. The battery isn't the best in the world. And note here, when I disconnect, we get a spark. We'll come back to that a little bit later. Okay, I got an idea. We've got 230 volt mains voltage here. I'm going to put that across the transformer. We've got around about a 2 ohm coil. 130 divided by 2. That's 115 amps. Let's give it a try. This is going to be epic. So here we have our transformer again. It's connected up through this little meter unit here that will measure both our voltage and our current together. And it's connected to the 230 volt mains. So don't try this at home. This is a highly trained stunt transformer. Let's turn it on and see what happens. That's 18 times less than I got with a 12 volt battery. Well, that's a bit odd and disappointing. We have a voltage of 238 volts, and we divide that by the current of 0.29 amps. We've got a resistance of 821 ohms. But I proved before it was 1.8 ohms. What's going on? Inductance. Okay, I admit it. That transformer was never going to pull 115 amps. First of all, I'm not actually that stupid. And the power point over there is only rated for 10. The transformer is actually designed to go onto a 230 volt circuit, so again, it was never going to pull that sort of current. But why didn't it pull that current? We already proved it has a resistance of 1.8 ohms, and we proved that Ohm's law is correct. At 12 volts it pulled out 6 amps. It's the inductance of that transformer that is saving it from exploding. So what is an inductor? Well, simply put, if you take a piece of metal and wrap some wire around it, you've created an inductor. And you might remember making something like this at school. Take a 1.5 volt battery, connect it up to your bit of wire, and you created a very nice little electromagnet. I know I made quite a few of those when I was at school, and they are the basics of electric motors. Without that basic principle, these stepper motors wouldn't work. So now we're going to introduce a new piece of terminology. Impedance. What the hell is impedance? Well, again, it's exactly what it sounds like. It is an impedance. It impedes. It's like a resistance which resists, and effectively they are pretty much the same thing, except impedance exists in AC circuits, whereas resistance exists in both AC and DC circuits. Impedance is totally frequency based. So if you have an inductor of a certain inductance, depending on the frequency that you feed into this, its impedance will change. The higher the frequency you feed into this, the higher the impedance, and therefore the higher the effective resistance. So for our transformer, when I used a DC battery which has no frequency, there was no impedance, and therefore Ohm's law kicked in and it drew 6 amps. Once I connected it to 230 volts 50 hertz mains voltage, it has a frequency of 50 hertz, 50 times per second. That signal, the power changes its polarity. The impedance of that transformer, or the inductance of that transformer, kicked in and created an impedance of 820 ohms, and that resisted the flow of current in our circuit, for which I'm immensely grateful. So is there a water-based analogy to this? And yes, it is. If you take some water and put it into a bucket, or maybe better still, stand in a swimming pool. Take your hand in a swimming pool and swish it about backwards and forwards slowly, and you'll feel a certain amount of resistance to that movement. Now do it quickly as you can, and you'll suddenly feel how much harder that water is. It's really trying to resist you. The frequency at which you move your hand backwards and forwards determines how much resistance you're going to feel in that water. And in extreme cases, if you plummet from an aeroplane into that water, it's going to feel like jumping onto concrete surface. So water can be hard or soft, depending on how quickly you try and enter it. So what has this got to do with anything? Well, let's look at our stepper motor. What is it? Well, basically it's an iron core with windings wrapped around it, just like my little electromagnet here, and just like my transformer is. It therefore has impedance to any AC signal, and these motors are driven by an AC signal. And if we want these motors to turn faster, we have to increase the frequency of that signal. Now it becomes clear that if we increase the frequency of that signal, the impedance of the motor increases, i.e. the resistance to the current flow increases, which means less current will flow in the motor, which means that the coils do not energize properly in the motor here, which means it gets weaker. The faster you turn the stepper motor, the weaker it becomes. And that is the real problem with stepper motors. So fortunately, stepper motor driver manufacturers have a cunning idea. You'll notice here on my stepper motor it says DC 6 volts, 1.2 amps. What that means is if I take a 6 volt battery and stick it across my windings, a current of 1.2 amps will flow through my motor here. And if I do that, the motor will not burn out. Now when you get your stepper motor drive, the first thing you need to do is set the current to match the motor. And the stepper motor driver's job is to provide that amount of current to the stepper motor. Now one thing you'll notice is the voltage you provide your stepper motor driver will be far in excess of the 6 volts it says on the motor here. It might be something like 50 volts or 70 volts. And the stepper motor driver's job is to provide the rated current that you're told it. So we know that current times resistance equals voltage. And we know that the resistance changes as a stepper motor increases its speed. So at a slow speed it will present a certain amount of resistance, and if you multiply that resistance by the current, you'll need a certain voltage for that amount of current to flow into the stepper motor. But as the stepper motor increases its speed, so will its resistance, which you multiply by the current, and you find I need even more voltage. And that's why we provide the stepper motor driver with that higher voltage. But sooner or later, you're not going to have enough voltage to keep supplying the amount of current you need to the stepper motor. That's a rather simplistic way of looking at it, because there are other forces involved here as well. But it gives you an idea of why our stepper motor drivers have such high voltages compared to what's written on our motor spec sheet, why we need to set the current on our stepper motor driver, and just roughly how the thing works. Having that higher voltage is quite important, and that's why when you see a stepper motor drive combination with very low voltages supplied to them, and I'm talking about the 24 volt ones to start with on the likes of eBay, they're not going to drive those motors very well. They're going to run out of that voltage they need to supply to the motor a lot faster than one being supplied with, say, 50 volts. So you can see how voltage is important in this equation as well. So here I am with my Gecko G540 drive, and I decided I want to buy a stepper motor for it. Now I went on eBay and looked up a couple of motors, and I found two of them here with exactly the same holding torque. So the first one here says it requires 3.5 amps. Well, that's just brilliant, because this stepper drive can provide 3.5 amps. But it has an inductance of 6.4 millihenries. Now on my website I'm going to put a spreadsheet that you'll be able to put these figures into, and it will tell you what sort of voltage you should be looking at to drive the stepper motor properly. And when I put that figure into it, it comes up with a figure of 81 volts required to drive it. And unfortunately, my Gecko drive can only provide a maximum of 50 volts. So it really would be a very poor match for my drive. Fortunately, I found another stepper motor. It has an inductance of 2.5 millihenries, and when I insert that figure into my spreadsheet, it pops out with a figure of 51 volts. Well, that's pretty good. This can provide 50 volts, 51 volts. That's close enough for me. Doesn't need to be exact, just roughly right. But hang on, it requires 5 amps. So it's going to be well underpowered as well, because my drive can only provide 3.5 amps. There's quite a big discrepancy there. I'm not going to get decent power out of the thing after all. The thing about those two motors are they have exactly the same holding torque. So that's something to be aware of. Not only are you trying to get a motor that will match your drives, you have to be aware that if somebody says, oh, I'm just using a 400 ounce inch motor on my drive, you still need to go and check its specs, because not all stepper motors are the same. They may look identical and they may have the same holding torque, but internally they're completely different. And if you get the wrong one, it will not run properly on your drive. Now, I learned fairly early on about what happens when you get a mismatched stepper motor and driver combination. The motors on this machine I brought in a kit form that came with motors, drive and power supply, and it was a dog. I wasn't using it on this particular machine, but it was just horrible. It came with a 24 volt power supply, which was not enough to power the motors properly. The driver obviously wasn't that good if the maximum it could provide was 24 volts in the first place. And the machine was just an absolute dog to use. It would continually lose steps. It was completely unreliable. And it's enough to make you want to give up the hobby before you've even begun it. Remember, the stepper motor driver combination that you have is the one item you will take from one build to the next if you're upgrading your machine. If you buy something decent, you're going to have an enjoyable experience. Buy something cheap and cheerful, I can guarantee you, you will not be cheerful for very long. You'll end up throwing the damn thing away, or at least part of it, and have to replace those components. Now, in my case, I brought myself a Gecko G540. This wasn't available at the time of the other kit that I brought. In fact, the kit I brought was probably one of the better ones, to be honest. But technology has moved on. The Gecko drive, I can now provide my motors with 50 volts and the amount of current they require, and what a difference it's made. This machine moves more than 8 times quicker than it did before, and it'll go even faster than that. It's completely reliable, it never loses steps, it's an absolute pleasure to use. What a difference having a matched stepper motor driver power supply combination can make in this hobby. Now, I fully understand that a lot of people aren't going to be able to work out what sort of voltage they need to drive their stepper motor and what sort of currents they need on their power supply. So what I've done is I've created a spreadsheet which you can use. Just enter the inductance of your motor and the current rating of your motor, and it'll work out for you what sort of voltage you should be looking at for your drive and what sort of current requirements you need for your power supply. And that should be a good starting point for working out your requirements. So let's take a quick look at that spreadsheet. So the spreadsheet is based on this particular document here from Gecko Drive. They're a United States company that makes stepper motor drivers, and it's well worth taking the time to sit down and read this document. In here you'll find out how to calculate the maximum voltage for your stepper motor, how to work out its current, how to build your own power supply if you wish, and further down how to select the right stepper motor for your particular application. So I went through and I found this particular stepper motor on the internet. It's a 381 ounce motor. It has an inductance of 2.8 millihenries and it has a current of 3.5 amps. And I was thinking this would be a good match to go with my Gecko drive. I can now open the spreadsheet and start entering the figures. I've got 2.8 millihenries and 3.5 amps. And because I would put 4 of the same motors onto my drive, I'm just going to copy that to the other 3 motor drivers here. That gives us our figures down here, 54 volts and 9.3 amps. So now we've got those figures plugged into the spreadsheet, it's time to see how good a match they are to my Gecko G540 drive. And the first thing we're going to look at is the stepper motor current themselves, and they're 3.5 amps. Now the Gecko G540 will power any stepper motor rated up to 3.5 amps, so that makes it a good match. But we still have to take into account the voltage. Now the voltage, maximum voltage that the spreadsheet calculates is 54 volts, and that is a maximum. It doesn't mean you have to have that supply with that much, but the closer you get to it, the better it's going to work. So I did put a note there saying beware, make sure you don't exceed the maximum voltage rating of your driver, and that's important for here because this can only be fed with 50 volts or less. If I exceed 50 volts, I'll damage the drive. So in my case, I would buy a 48 volt switch mode power supply. It's a standard off-the-shelf power supply to run my Gecko drive and those motors. Now the discrepancy between 48 volts and 54 is very little. It's only 6 volts. There's a big difference between depriving a stepper motor of 6 volts and trying to run them on a 24 volt power supply and depriving it of 30 volts. That's why I say if you see those kits on eBay and they're trying to run them on a 24 volt power supply, I would turn around and run as fast as I could in the opposite direction. They will not run very well at all. Now, our next consideration is current. What size power supply do we need? How much current do we need it to supply? Now, according to the spreadsheet, we need 9.3 amps. Now, I know what you're thinking. We've got 4 3.5 amp motors. That's 14 amps. Well, according to Gecko, you only need 2/3 of that current, so that brings it down to the 9.3. And I'm tempted to think that if you're bright enough to make a drive as good as this, you probably know what you're talking about. So when it comes to choosing a power supply, I'd have a choice of a 48 volt 10 amp power supply or a 48 volt 12.5. And personally, I'd go for the 12.5. I don't like the idea of running a power supply close to its upper limit. So in this particular instance, the 12.5 would have that little bit of extra headroom and less stress on its components, because its components are rated to supply even more current. Whereas the 10 amp one, you're going to be running it close to its maximum and they're only rated for 10 amps. So personally, I'd go for the 12.5, though many Gecko kits are sold with a 48 volt 10 amp power supply and they run perfectly well. So for me, the ideal setup for me would be a 48 volt 12.5 amp power supply, my Gecko G540 drive, and 4 of those little 381 ounce stepper motors. And I reckon that would be a really sweet combination. Now if you're looking for that spreadsheet, just follow the link under this video. You'll be taken off to my website where you'll find the spreadsheet and also a link to the Gecko Drive website where you'll find that document. It's well worth taking the time to read. Educate yourself up as much as you can. Now the spreadsheet can use not only to assess Gecko drives, but for any stepper motor driver power supply combinations. The nature of stepper motors don't change just because you change the driver. With the information you've got, you'll then be able to assess any kit that you're looking at and decide whether it's massively underpowered, and if it is, ignore it and move on to something else. There are plenty of reputable kits available for sale. Now just remember as well, you're not going to find everything matched exactly right, just so long as it's close. It doesn't have to be exact, and just avoid anything that's just so wildly out that it's just ridiculous. Once you've found a kit you like, why not ask others who have the same kit what it's like and how well it runs? That's always a good indication. For me, the only experience of a decent driver I've got is the Gecko G540, and I run it with my 270 ounce motors and it runs really well. I'm really pleased with it. Well, I hope you found that interesting and maybe a bit more informed about stepper motors and driver combinations. At the very least, I hope the comatose state you've probably slipped into wears off shortly. All that remains me to do is to thank you for watching. Don't forget to like and subscribe, and check out my website, www.cncnutz.com. Until next time, cheers.